Hello, welcome to the Advanced Learning Unit of the module Architectural Design and Applications in IoT. In the core learning unit, we emphasized on software architectural styles that govern the communication interplay between, mostly, the edge and the server-side components of IoT systems. In this unit, we focus on the internal components of the server-side infrastructure and we discuss the subsystems involved in the data processing pipeline. This lecture is divided in three main sections. Firstly, we focus on the core and optional IoT solution architecture subsystems. Secondly, each architectural subsystem is discussed in detail, including the purpose of the subsystem as well as technology options for subsystem implementation. The last section focuses on implementation considerations of the IoT solution architecture. The subsystems of an IoT solution should be built as discrete services that are independently deployable, and able to scale independently. These attributes enable greater scalability, more flexibility in updating individual subsystems, and provide the flexibility to choose appropriate technologies on a per-subsystem basis. It is critical to have the ability to monitor individual subsystems as well as the IoT application as a whole. Subsystems may communicate over HTTPS using JSON, as it is human-readable, or binary protocols for high-performance needs. The discrete nature of the architecture also allows for a hybrid cloud and edge compute strategy, i.e., some data processing is expected to happen on-premise. It is recommended to use an orchestrator, as for example Kubernetes services, to scale individual subsystems horizontally, or PaaS services that offer built-in horizontal scale capabilities. At the core, an IoT application consists of the following subsystems: edge devices and /or on-premise edge gateways that have the ability to securely register with the cloud, and connectivity options for sending and receiving data with the cloud, a cloud gateway service, or hub, to securely accept that data and provide device management capabilities, stream processors that consume that data, integrate with business processes, and place the data into storage, and a user interface to visualize telemetry data, analytics, and insights, as well as facilitate device management. The core subsystems of the IoT application architecture are considered to be links in the chain of analytics data pipeline, a fundamental process that takes data from its source through several steps until it is available to analytics clients. Data does not end up nicely formatted for analytics and insights on its own. It takes a series of steps that involve collecting the data from the source, massaging the data to get it into the forms appropriate to the analytics desired, and ultimately pushing the prepared results to the location from which they can be consumed as notifications and actions. This series of steps can be thought of as a pipeline. The analytics data pipeline forms a basis for understanding any analytics solution. As shown in the figure, the data pipeline consists of 5 major components, which are useful in comprehending and designing any analytics solution. The source is the location from which new raw data is pulled or which pushes new raw data into the pipeline. For example, the edge devices can be seen as data sources. The ingest component is the computation that handles receiving the raw data from the source so that it can be processed. The processing component is the computation which controls how the data gets prepared and processed for delivery. The storage component is the location where the ingested, intermediate, and final calculations are stored. Storage can be transient, when the data lives in memory only for a finite period of time, or persistent, when the data is stored for the long term. Finally, the delivery component is involved on how the data is ultimately presented to the consumer, which can run the gamut from dedicated analytics client solutions used by analysts to APIs that enable the results to integrate into a larger solution or be consumed by other processes. The storage and processing subsystems together form a data lake. The term data lake is becoming the latest buzzword and is following a path similar to how big data grew in popularity, and at the same time its definition has become more unclear as vendors attach the meaning that suits their products best. So let's begin by defining the concept of a data lake. A data lake consists of two parts, storage and processing. Data lake storage requires an infinitely scalable, fault-tolerant, storage repository designed to handle massive volumes of data with varying shapes, sizes, and ingest velocities. Data lake processing requires a processing engine that can successfully operate on the data at this scale. In other words, data lake is a repository that intentionally leaves the data in its raw or least processed form to allow questions to be asked of it that would not be answerable if the data were packaged into a particular structure or otherwise aggregated. In reality, a data lake includes not just a single processing engine, but multiple processing engines, and because it represents the enterprise-wide, centralized repository of source and processed data, it has other requirements such as metadata management, discovery, and governance. Let us look at two different architectures that can be used to act on the data managed by a data lake, Lambda architecture and Kappa architecture. Lambda architecture was originally proposed by the creator of Apache Storm, Nathan, in order to reduce the complexity seen in real-time analytics pipelines by constraining any incremental computation to only a small portion of this architecture. In Lambda architecture, there are two paths for data to flow in the pipeline. A hot path where latency-sensitive data flows for rapid consumption by analytics clients. For example, the results need to be ready in seconds or less. The hot path analyzes data in near real time, as it arrives. The objective of the hot path can be summarized as, trade off some amount of accuracy in the results in order to ensure that the data is ready as quickly as possible. A cold path where all data goes and is processed in batches that can tolerate greater latencies, as for example, the results can take minutes or even hours until are ready. The cold path performs batch processing at longer intervals, as for example hourly or daily. The cold path typically operates over large volumes of data, but the results don't need to be as timely as the hot path. The objective of the cold path can be summarized as, take the time you need, but make the results extremely accurate. The Lambda architecture consists of 3 layers, and each of these layers can be made using various technologies. The batch layer stores the master copy of dataset and computes arbitrary batch views. The batch layer allows batch processing for pre-computation of large amounts of datasets. It provides the managing of the master dataset, a set of immutable, append-only, and exclusive raw data, but also provides a pre-computation of arbitrary query functions, called batch views. This layer doesn't update regularly batch views, which lead to latency. The streaming or speed layer means computing in real time by performing latency-sensitive calculations as data arrive. Results are then exposed as real-time views. The serving layer integrates results from the batch and speed layer. This layer responds to queries and provides calculation results. Analytics clients can consume the data from either the streaming/speed layer views or the serving layer views depending on the time frame of the data required. In some implementations, the serving layer can host both the real-time views and the batch views. Kappa architecture surfaced in response to a desire to simplify the Lambda architecture dramatically by making a single change, eliminate the cold path, and make all processing happen in a near, real-time streaming mode. Recomputation on the data can still occur when needed, it is in effect streamed through the Kappa pipeline again. The Kappa architecture was proposed by Jay Krebs based on his experiences at LinkedIn, and particularly his frustrations in dealing with the problem of code sharing in Lambda architectures, that is, keeping in synchronized the logic that does the computation in the hot path with the logic that is doing the same calculation in the cold path. In the Kappa architecture, analytics clients get their data only from the streaming/speed layer, as all computation happens upon streaming data. Input events can be mirrored to long-term storage to enable recomputation on historical data should the need arise. As in most cases, it can be said that there is no single optimal solution for all problems, which is usually defined by the term one size does not fit all. Lambda architecture is more versatile and is able to cover a greater number of cases, many of which require even real-time processing. One question that we must ask ourselves in order to decide is the analysis and processing that we are going to carry out in the batch and streaming layers the same? In this case, the most appropriate option would be the Kappa architecture. We will also lean towards a Lambda architecture if our batch and streaming algorithms generate very different results, as can happen with heavy processing operations or in machine learning models. In the view of the Lambda architecture, the core subsystems of the IoT application architecture are shown in this figure. The stream processor along with the warm storage lie within the warm path, which can be also called fast or real-time path. On the other hand, the batch processor and the cold storage lie within the cold path, which is also known as slow or offline path. In the view of the Lambda architecture, the core subsystems of the IoT application architecture are shown in this figure. The stream processor along with the warm storage lie within the warm path, which can be also called fast or real-time path. On the other hand, the batch processor and the cold storage lie within the cold path, which is also known as slow or offline path. In addition to the core subsystems, many IoT applications will include subsystems for intelligent edge devices, which allow aggregation or transformation of telemetry data, and on-premise processing, cloud telemetry data transformation, which allows restructuring, combination, or transformation of telemetry data sent from devices, machine learning, which allows predictive algorithms to be executed over historical telemetry data, enabling scenarios such as predictive maintenance, and user management, which allows splitting of functionality amongst different roles and users. There are multiple cross-cutting needs for IoT applications that are critical for success, such as security, logging and monitoring, and high availability and disaster recovery. Security is a critical consideration in each of the subsystems. Protecting IoT solutions requires secure provisioning of devices, secure connectivity between devices, edge devices, and the cloud, secure access to the backend solutions, and secure data protection in the cloud during processing and storage. Logging and monitoring for IoT application is critical, determining system uptime and troubleshooting failures both for individual subsystems and the application as a whole. High availability and disaster recovery focus on ensuring an IoT system is always available by rapidly recovering from systemic failures. The technology used in IoT subsystems has different failover and cross-region support characteristics. This may result in hosting duplicate services and duplicating application data across regions depending on acceptable failover downtime and data loss.